Hello students, in this video we are going to discuss about electric energy, power, combination of resistors, series combination and parallel combination, of resistors. Before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you need the notes of this chapter in the form of PDF, then send your phone number. This is my Insta ID OJHALAKHYAJIT123. This is my Insta ID. Then you can send your phone number. You can message me on Insta. You can send your phone number so that I can provide you the PDF of this chapter, notes of this chapter, right? So let's start. So first let us discuss about electric energy. So here I'm going to explain only, okay? So if you need the notes, then send the message, okay? So I'm not going to write each and everything here. I'm going to give you the explanation, okay? So now you see, so what do you mean by electric energy? Suppose we have a circuit element. Suppose this is a resistor of resistance R, right? And potential difference across it, suppose B. Potential difference across it, suppose B. Let me consider that way. And in time t, Q amount of charge is flowing through this element, okay, from A to B, suppose, right? From A to B. Then current through this element that will be given by I is equal to Q by T, which is where Q is equal to I into T, right? Q is equal to I into T. Now you see, so as I have considered that V is the potential difference between these two ends across the elements, this resistor R, right? And then you see the work done to carry Q charge across this element will be given by W is equal to V into Q, because you see, according to the definition of potential difference between the 2 points is given by the amount of work done required to carry 1 coulomb charge, right? If suppose, let me consider that W amount of work is done to carry Q coulomb charge from this end to that end, then potential difference between these two is V is equal to W by Q, right? V is equal to W by Q. So if that is the relation between the work done and potential difference, then W must be equal to V into Q, right? So W is equal to V into Q, and Q we have already got that I into T, so that's why we can write V I T, okay? So this work done is nothing but electric energy, because we know energy is equivalent to work done, right? So this is nothing but our electric energy, V I T. And again, from Ohm's law we know that V is equal to IR, right? V is equal to IR. So we can replace this V by IR, then we can write this relation in this form as well, I square R into T. And again, you can replace this I also by V by R, right? Then if you replace this I by V by R, then you're gonna get this relation that E is equal to V square by R into T. So this is another form of another form, okay, of electrical energy. So hope you have understood this. Similarly, power. So let me clean these things. So let us discuss about power, okay? Now you see, okay, power is, we know that rate of doing work. Now here you see W by T, and work done we have got that V I into T. This is the expression for work done, which is equivalent to energy. This is equivalent to energy, right? So work done by T. So T cancels. So power is equal to V into I. That's what we have got. Again, you can see that we have got different forms of we have got this energy in different forms. Okay, these are different forms. If you use these forms, then what you're gonna get? So you can replace this W by this relation also. V square by R into T. So then you will get P is equal to V square by R. Okay, so if you use this relation, then I square R into T, then you will get P is equal to, then you will get P is equal to I square into R. That's what you will get. So these are different relations for power, different form, right? So hope you have understood this. So hope you know the SI units of these quantities. For energy, SI units of energy, obviously you know joule, right? And power, so power is work done by time, so that's why it must be SI unit of power. That's why it will be joule per second, right? So hope you have understood this. So now let us discuss about series combination and parallel combination of resistors. Okay, now you see series combination. Right? Suppose we have let me consider 3 resistors. You can consider more. Okay, more than 3 also you can consider. So let me consider 3 resistors of resistance R1, R2 and R3. So V be the potential difference across it, and I be the current. Okay, so when we connect the resistors in such a way that current flows through its resistor is equal, then that combination is said to be series combination, right? But here potential across these resistors will be different. Across R1 suppose V1, across R2 suppose V2, across R3 it is suppose V3. Okay, potential difference will be different here, because you see this end of this resistor R1 is connected to this battery directly, but this end is not connected to this negative terminal of this battery directly. Okay, this end is connected to one end of this R2 resistor, right? So hope you have understood the reason behind it, why the potential difference across each resistor is different in case of series connection. So but here the path is same, so the current will be same through each and every resistor, right? So now you see, when they are in series combination, then the then the effective resistance or the equivalent resistance, let us say it is RS is the equivalent resistance, because to represent the series connection I have written here RS, so that will be given by R1 plus R2 and R3, right? So let me show you how. Now you see, so potential difference across R1 is suppose V1. So then V1 is equal to, given by according to Ohm's law, V is equal to IR, right? V is equal to IR. So here V1 will be equal to I R1. Similarly V2 is equal to I R2. Similarly V3 is equal to I R3. And so V, that is the potential difference across this combination, will be given by V1 plus V2 plus V3. So that must be I R1 plus I R2 plus I R3. So that will be equal to, so if you take the I common here, then it's gonna be equal to R1 plus R2 plus R3, right? Now if we consider the effective resistance, the total resistance is RS, then according to Ohm's law this V must be equal to I into RS, right? So we can write this V, instead of V we can write I into RS, then I cancel, so RS is equal to R1 plus R2 plus R3. That's how we can find the equivalent resistance in series connection. If we have n number of resistors, then then Rs will be equal to R1 plus R2 plus dot 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 plus Rn. We have to add all this. So now let us discuss about parallel connection, right? So parallel combination. Now let us consider three resistors. Suppose this is R1, R2 and R3. Okay. Now let us connect those resistors in such a way that potential difference across each resistor is equal to the applied potential difference across the combination, right? So here you see in this combination you can see, let me use another ink. So end point of these two are connected to this terminal, positive and negative terminal of this battery, right, directly. Similarly, end point of this resistor also are connected to this battery, right? Similarly, end point of this R3 are also connected to this, battery directly, right? So that's why, so the applied voltage and the voltage across its resistor will be equal. So across R1 also V, across R2 also V, across R3 also V, because here you see these these two endpoints and these two endpoints of this resistor and these two endpoints of these resistors are all the endpoints of the all resistors are connected to this battery directly, right? Hope you have understood this. But here you see, if I current flows through this circuit, then as this part is split into three different parts, so here we're gonna get I1, I2, I3, three different currents through three different branches, right? So now if we connect these resistors in such a way that the potential difference across each resistor is equal to the applied potential difference, then this combination is said to be parallel combination. Okay, so in 2025, so in HS final examination under Assam Higher Secondary Education Council in 2025, question was asked on parallel and series combination. Maybe I think as short notes, you were asked to write short notes, I think. Okay, so very important topic. So now you see, so in this case the effective or the equivalent resistance, let me write here Rp, that will be given by 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Okay, that's how we used to calculate. Then we have to take the reciprocal of this 1 by Rp, then you will get the Rp, right? So now you see here current is different but potential difference is same, right? So according to Ohm's law, so here we're gonna get you see current through R1, so I1 is equal to V by R1, I2 is equal to V by R2, then current through this R3 resistor I3 is equal to V by R3. So total current is I, so I is equal to V by R1 plus V by R2 plus V by R3. If the effective resistance is Rp, then this I must be equal to V by Rp, right? So here you can take V common. So if you take V common, then what you're gonna have 1 by R1 plus 1 by R2 plus 1 by R3, right? So here V cancels, so we get 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3, right? So that's how we used to find the equivalent resistance of parallel combination, right? So hope you have understood this.